Everyone. This is going to be the second lecture on norms and trace, and the goal is basically to relate the computations of norm and trace to some Galois theory. So let me remind you of our overarching goal with this stuff on norms and trace. Why should you care? So the goal is to prove that rings of integers So I want to prove that rings of integers are finitely generated Z-modules. So finitely generated abelian groups. And to do this, we need, in particular, we need trace. To do this, we need trace. Okay. So in this lecture, we're going to basically explain how you can use Galois theory to compute the trace of an element. So maybe I should remind you what this trace is. Recall, I'll just do it in the field case. If L over K, an extension of fields, I guess probably a finite extension. Finite extension of fields. And let's say beta 1, beta n is a basis for L over K. And let's say alpha is in L. Then we can make a matrix, an m by n matrix. So basically the matrix is going to be the multiplication by alpha matrix, where, okay, so maybe I'll tell you what the matrix is going to be Aij, and it's going to have entries in K, where alpha times beta I is the sum over Aij, j equals 1 to n beta j. So essentially, it's the multiplication by a alpha matrix. Then the trace from L over K alpha, this is the trace of this matrix. It should not be alpha ij, this should be aij. Trace is the trace of this matrix, and the norm is the determinant. Okay. And last time we did a few examples and we talked about how this doesn't actually depend on a choice of basis and so on. So these are what the trace and norm are. And the goal in this lecture is to relate these ideas to a little bit of Galois theory. So the overview. So the first thing we're going to do is we're going to prove something called we're going to basically sketch the proof of the transitivity of norm and trace, which is kind of something I talked about very briefly last time. Transitivity of norm and trace. Okay, we're going to prove something that relates the trace and the norm to the minimal polynomial. So trace, norm, and the minimal polynomial. As a corollary to 2 here, we're going to get that trace and norm preserve integrality. So the trace of an integral element is integral over k and so on. So trace and norm preserve integrality. Something maybe I should mention here is that, yeah, I guess this is kind of clear, but these will be elements of K because these matrices have entries in K. So the trace from L to over K and the norm from L over K will be elements of K, or whatever your base ring is. So the third thing we're going to prove, it'll follow from 2, is that trace and norm preserve integrality. So the trace of an integral element, the trace of an element integral over K is still integral over K. And the fourth thing, which is kind of like the big topic here, is that the norm is essentially, so it's not quite, there's like a scalar, but essentially the product of the Galois conjugates while the trace is the sum. Okay. So I'll be more explicit about what I mean by essentially here, but this is kind of the relation between norm, trace, and Galois theory that the whole lecture is really focused on. Okay, so let's go ahead and start with the transitivity of norm and trace. So what do I mean by this? So lemma, this is 18.1. We're going to let, let's say, K be contained in L, be contained in M, be, let's just say, finite extensions of fields. Then we're going to say basically the norm from M to K, so the big norm, is basically the composition of the two smaller norms. So the norm from L to K composed with the norm from M to L. Okay, and the same thing holds for trace. Okay, how do you prove these? Proof. So I'm not going to actually go through the whole proof, but the hint is as follows. If alpha I equals 1 to n is a basis for L over K, and beta, so I equals 1 to little m, is a basis for m over L, then I can just take the product alpha I, beta j, 1 less than or equal to I less than or equal to n, 1 less than or equal to j less than or equal to m, and this will be a basis for m over k. Okay, and then given like an element gamma, you can use all three of these bases to compute each of these respective norms or traces, and you'll find that equality holds. So compute norm slash trace with respect to each basis and compare. So there is work to be done here, to be clear, but it's not too bad with respect to each basis. And compare. Okay. So this is one. The norm and the trace are transitive, which means that if I want to compute the norm of a big extension, I can split it up into two smaller extensions and compute the norm first. Basically compute the successive norms all the way down to the base. Okay. So the second thing here is the trace norm in the minimal polynomial. So this is going to be 18.2, this proposition. We're going to let L over K be a field extension let's say of degree n. And I'm going to let B and L have minimal polynomial say F over K. And so we can enumerate the roots of F. F, let's say, with multiplicity. So if I have a repeated root, it will appear twice in this list, or at least it'll appear if I have a repeated root, let's say of degree 2, of multiplicity 2, then it will appear twice in this list. With multiplicity, let's say B is equal to the first thing in the list, and then I've got B2 all the way up to Bm. Then, so I've got this list. The trace okay, B is R times, so maybe I should tell you what R is. For R equals N divided by M. The trace of L over K. B is R times the sum of these guys, so beta 1, beta M, and the norm is the product to the rth power. This should be, I screwed up here. These should be B's. Okay. So, what is it saying? It's saying that the sum of the roots of f are almost a trace, and the product of the roots of f are almost a norm, except for there's like some constant factor going on here, which has to do with whether f has like repeated roots, and the number of roots of f in relation to the degree of the field extension. Okay. So basically the thing you want to do is reduce to the case when L is K joint beta. This is the idea. Note. Okay. So basically by the lemma we can reduce to this case. So by the transitivity, so how do we, by transitivity of norm and trace, I claim it suffices to show norm L over K, or sorry, not norm L over K, norm K joint beta, K joint B over K of B1 through, Jesus Christ. The norm of K joint beta of B is the product of these guys. So how do we prove this? Well, we have, so assuming this, and I guess there should also be a statement about trace, and trace. I'm just going to focus on norm for this. The proofs for norm versus trace are always like almost identical. So if I know this, then we have, let's say, the norm from L over K of B. Well, this is the norm from K join B to K of the norm from L to K join B of B. Okay. And we talked about this last time, but if your element already lives in the base field, then the norm just multiplies it by the degree of your field extension. So this is the norm from K join B over K of the degree here, L over K join B times B. Okay, or wait. Oh, sorry. Okay, I screwed this up. Then the norm doesn't multiply it; exponentiates by that power. Okay, so this should really be B to the power of the degree L over K join B. Okay. So since B already lives in K join B, this norm is just this. The norm is multiplicative, so this is going to be the norm of K join B over K of B all to the power of the degree. Okay, since we're assuming this fact here, this is B1 Bm all to the power of this extension. Okay, and how do we, what's the degree of this extension? Well, note degree of our polynomial f. Well, f has m roots counting multiplicities, so this has degree m. So the degree of K join B over K equals m, and the Tower law, so by the Tower law, this degree is n over m, which is r. Okay, so it suffices to show in the case when L equals K join B, and in this case we can basically use like we can compute this norm directly, more or less. Okay, so without loss of generality, L equals K join B. Okay. Then 1 b to the m minus 1 forms a basis over K, and let's say if f equals sum of ai x to the I equals 1 to n, where an is 1. am, sorry, this should be m because it's the degree of our guy. Then I can compute the matrix of B in this basis. The matrix of B is 0, 1, 0, 0, 1. So this is like some direct computation that you should check on your own. So it continues in this way. So this off diagonal is just a bunch of ones, and then the last column is the negative coefficients. A sub m minus 1. Okay. And there should be like the second to last column is zeros, except for at the very end there's a 1 here. Okay. So this is the matrix of B in this basis. This basis. Okay. And from here I can tell you what the trace and the norm are. So the trace, then the trace is, sorry, this should be negative am minus 1, which is, so you need to remember that the coefficients of the minimal polynomial are the like alternating sign of the sum of the roots and stuff like this. It's like symmetric polynomials in the roots. So negative am minus 1 is the sum of the roots. And the what do I want to say here? The trace and the norm is, so you'd compute the determinant of this matrix, which is negative 1 to the m times a naught. So if you, it's the easiest way to explain how to compute the determinant of this matrix. I guess, I mean, it doesn't matter. Just spend some time thinking about what it would look like expanding along any of these rows or columns, and you'll find this. And this is the product of the guys. So if you're skeptical about either of these two claims, so if you're skeptical about this, or if you're skeptical about this, you should think about f as a product of x minus bi. I equals 1 to m. And think about, you know, the constant term is going to be the product, like, yeah, just think about what happens when you expand out this product. Okay. So there's this first useful fact, and you can already kind of see the sums of Galois conjugates and the product of Galois conjugates kind of coming up here. So before I prove the actual Galois theory statement, we're going to need to recall some important facts. Okay. So let's go ahead. There's going to be 3 key facts. So key fact 1. And I'm not going to prove any of these. They're mostly statements from field theory or Galois theory that, if not familiar, should be at least something that you are like comfortable to take as a black box. Okay. So let's go ahead and give you key fact 1 here. So So if omega over k is Galois, and f in k given x is irreducible, and let's say it has a root in omega, then the Galois group acts transitively on these roots. Okay, so this means that essentially for any root of f, for any pair of roots of f, basically, I can find an element of the Galois group which sends one root to the other. Okay. So this is key fact 1, key fact 2. Okay. Key fact 2 says that we're going to let's say omega over k be algebraic, and let's say L is, or sorry, not L, K is contained in some algebraically closed field okay, then any embedding sigma from K into F extends to omega. So essentially the way I think about this is like I'm imagining K, basically each sigma is a way to view K sitting inside F, and for each sigma we also have an analogous omega sitting above K inside F. Okay. And then key fact 3 says that, so E over F, let's say this is going to be a separable extension of degree n. Okay, then what can I say here? I've got a separable extension of degree n, and furthermore I've got a Galois extension of f, and the number something is not quite right, of f homomorphisms. So I'll state what I have written down, but it's definitely not right. The number of f homomorphisms sigma from E to omega is n. Okay, so the reason I know this isn't right is because if I take omega equals f, then I shouldn't expect any f homomorphisms from E to sigma if this thing is like some big field extension. Okay, so something is not quite right here. I think I need to know something more about omega. I think, okay, I can change this to be like this. So roll extension of degree n. Okay, I can change this to be e over f be a separable extension of degree n. If let's say omega is a Galois extension not of f but of e. Then the number of f homomorphisms. Say sigma from e to omega is n. Okay, so I think this is actually the statement that I want. And the reference, so the reference is proposition 2.7 part A in Milne's notes. On field theory. Okay, so these are the 3 key facts I'm going to need to prove the following theorem. So the theorem is as follows. We're going to let L over K be a separable extension of degree n. Okay, and then we're going to let omega be a Galois extension, let's see, of L, and sigma 1, sigma n. Distinct K homomorphisms of L into. So that the reason we know this this is n is by this key fact 3. So we're already using key fact 3 here. Okay. Then what can we say? And the trace is the sum of these Galois conjugates. So for beta in L. Trace is the sum of these guys, and the norm is the product. Okay, so the idea is essentially that basically you want to use this previous proposition 18.2. This should be 18.3. And try to leverage essentially this previous proposition. Okay, so there are a few steps here. So steps. So I guess the first step, we're going to define something. So we're going to define S sub I. This is going to be, so I guess, okay, maybe we're going to let beta 1. Okay, we're going to let f be the minimal polynomial of beta over k and beta 1 through beta m, or yeah, beta m. Gosh dang it. Yeah, beta m be the roots of f. Okay, and we're gonna let s of I be the collection of sigma I such that sigma I of beta, and I'm gonna assume this first one is beta, is beta I. Okay, so it's the elements of this, the embeddings of L into omega, which send beta to beta I. Okay. So there are a few facts you want to prove about these S of I's. One is that they all have the same size. So the size of S1 is equal to S sub I for all I. Another fact is that basically these guys what do I want to say? The collection of these embeddings is exactly a disjoint union over these SI. So each embedding has to send beta to some beta sub I, and there's no overlap. So proof. So we prove. So I guess first, assuming we know like 2 and 3 here, and 3, we prove the proposition. Okay. Note that the size, so if I take m and I multiply by s1, okay, well there are m of these s sub i's, so this is I, because there are m roots. There are m of these s sub i's, so I guess distinct by separable hypothesis. Okay. Since L over K is separable, these all have to be distinct. And m times s sub 1 is, well, there are m of these and they all have the same size. So this is the sum of the sizes of the s sub i's. I equals 1 to m. Okay, and this is exactly the size of these sigma sub j's, and by key fact 3, this is n. Okay, so what does this tell me? This tells me that the size of s sub 1, and really the size of each s sub I, is equal to n divided by m, which is, we're going to call r from before. Okay, then the trace of this guy over k of b, well, this is just going to be by the previous proposition by 18.2, r times b1 plus r times b2 beta 2 plus that r times beta m, and this is exactly the sum of these Galois conjugates. Okay, so there are, if you want to explicate this step more, break up this sum based on whether these guys are in S sub I, and then you'll see I have R of these guys sending me to beta 1, R of these guys sending me to beta 2, R of these guys sending me to beta 3, and so on. Okay. And then similarly for the norm. Okay. So the final thing, it remains to show 2 and 3. Okay, so to show 2, essentially 2 is where most of the work is. Okay, 3, so note, I'll just write it down now. 3 follows from the fact that since sigma sub I fix k, they must permute the roots of f of a polynomial over k. Hence, for each I, sigma of beta sub I equals, or sigma of beta has to be some root. It's beta sub I for some I. Okay, and the disjointness follows from the fact that these, so roots are distinct. Disjoint follows from distinct roots. Okay. So how do we prove 2? So this is where the real work is. So first we're going to show each is non-empty. So first, by key fact 1, gal. So I want to see. So essentially what I want to say here is that the Galois group acts transitively. Acts transitively on the roots of f. Okay. So if tau and gal omega over k sends, let's say, beta to beta sub I, then tau restricted to L sends is a k homomorphism. From L into omega sending beta to beta sub I. Hence, tau restricted to L is in S sub I. Okay, so each S sub I is non-empty. And the idea from here is to basically construct an injection from S1 into Si And then by symmetry, basically, the equality of these sizes will hold. Okay, so thus each xi, each si is non-empty. So next we're going to show each embedding of L into omega is what do I want to say? Extends to omega. Okay, and we're going to use key fact 2 for this. So we have for sigma sub I from L into omega, we can put this into the algebraic closure. Okay, then sigma sub I extends to, let's say, sigma sub I tilde from omega into omega bar, okay, by key fact 2. Okay, I guess maybe I should assume omega is a finite Galois extension. So I guess it doesn't need to be finite, it just needs to be algebraic. So ignore this by key fact 2, period. I guess maybe omega over L is algebraic. Okay, and then since omega over L is Galois, these actually have to have image contained in omega. It's actually contained in omega. Okay, these things, I guess really this should be not omega over L, but omega over k. But that follows from the fact. So yeah, there's kind of like a sequence of logic that I'm maybe omitting here, which is omega over L, Galois. So this is by hypothesis. This implies omega over k Galois, which implies that since sigma sub I tilde is a k homomorphism, sigma sub I tilde of omega is contained in omega. Okay. So we've got thus really in reality this is a map from omega to omega, and it extends sigma sub I. Okay. Now we're going to use basically key fact 1 again to prove that each S sub I has the same size. So thus every embedding of k into omega extends to, sorry, this should not be k, this should be L, of L into omega extends to an automorphism. Omega to omega. So given sigma sub j and S1, lift to tau sub j and from omega to omega. Choose, let's say, var phi sub I in the Galois group over k, sending beta 1 to beta sub I. We can do this by transitivity, so this is key fact 1 again. Key fact 1. Okay, then send sigma sub I, or sigma sub j, sorry. Sigma sub j to var phi sub I composed of tau sub j restricted to L. Okay. Okay, so there's, I claim this is an injection. Okay, so essentially, if var phi sub I composed of tau sub j restricted to L equal some var phi sub I composed with tau sub j prime restricted to L. So let's see here. Maybe not tau sub j prime, it should be like tau sub k or something. Tau sub k restricted to L. Then since var phi sub I is injective, this is not a morphism. Okay, then tau sub j restricted to L would equal tau sub k restricted to L, which implies that sigma j equals sigma k. Okay, so this is proof of injectivity. This is sufficient by symmetry. So what do I mean by this sufficient by symmetry? I mean that you could like just as easily construct this injection from S sub I to S sub 1. So you could just as easily the injection from S sub I to S sub 1. Okay. So thus, the size of S sub I equals the size of S sub 1 for all I. Okay, and this finishes this long and complicated proof. So what's the moral here? The moral is essentially that trace and norm are closely tied to the product and the sum of Galois conjugates. And I guess maybe I should remark, I only proved things for trace here. The proofs for norms are very similar. Okay, I've kind of swapped around the two things. So I want to end with this trace and norm preserve integrality. This won't be too bad. So corollary let L over K be a finite extension of fields. Let beta and L be integral over K. Or, sorry, over, let's say, A subset of K, an integral domain. And maybe I need, let's say, A is, oh, no, I don't need this. Okay, then, what can I say? Trace from L over K of beta and norm from L over K beta are integral over A. Maybe I actually do need this. Proof. So the idea is to use this 18.3. So however, I think it doesn't. So maybe I need an added assumption here. Be an integral domain. Suppose A is integrally closed. So the issue is I want to use the fact that the coefficients of the minimal polynomial are in A. Or, oh. Yeah, no, okay. We'll just do this proof because I know how this one will work. So suppose A is integrally closed, then let me actually just go ahead and erase this stuff here. Integrally closed, then trace L over K beta norm L over K beta. These actually lie in A. Okay, and the proof is really short now. So trace beta is the, I guess maybe we'll say trace and norm are both coefficients of the minimal polynomial. Of beta over K, which, as A is integrally closed, lie in A. Okay, so this here is 18.2. I'm using that pretty directly, and this is the lecture on the integral elements and minimal polynomial. Let's see. Lecture on integral elements and minimal polynomial. Okay. So this pretty much wraps up this lecture. Okay, and I'll see you in the next lecture where we talk about bilinear forms.